On behalf of the Department of Animal Science, I want to welcome you to the 15th H. Allen and Ann Tucker Lecture. So just a little background, every year we have some new people that maybe didn't know Dr. Tucker or didn't know his whole story. So just a little bit about him. Herbert Allen Tucker was professor of animal science and physiology here at MSU from 1962 to 2000. During that time, he became the leading expert on mammary biology and lactation in dairy cattle. He earned his BS in animal husbandry from the University of Massachusetts in 1958 and his MA and PhD from Rutgers in animal physiology in 1960 and 1963, respectively. In his scientific career, he authored 355 publications, and one of his more impactful ones was his co-authorship of a book called Dairy Cattle: Principles, Practices, Problems, and Profits, which became the most popular college textbook for dairy science. So one thing that stood out about him is he was known as really a basic researcher, and yet he had this aspect of being very interested in application on dairy farms. His work in the field earned him the Sigma Xi Research Award at MSU, the MSU Distinguished Faculty Award, and an Upjohn Physiology Award from the American Dairy Science Association, and then the Casado Award for his work in graduate training, which he probably appreciated as much as any of the others. Today we're fortunate to have with us Ann Tucker, as well as Hannah, Glenn, and Brittany, who all work in dairy science in one way or another. And then, of course, Eva, who is in training still. So thank you all so much for being here. It means a lot to us. So this year, we're honored to welcome a distinguished scientist who has had a career that's kind of mirrored Dr. Tucker's work, more so than many of our past speakers in this series. Working in physiology and endocrinology of lactation. So Dr. Rupert Bruckmaier joins us today from the University of Bern in Switzerland. Originally from Germany, Rupert completed his bachelor's and his doctorate degrees at the Technical University of Munich before working as a research associate at the University of Bern for 10 years. He then moved back to Munich to work as a senior scientist for 7 years, and then back to the University of Bern, where he became the head of veterinary physiology in 2005. And he held that position until 6 weeks ago when he retired. So congratulations on your retirement. Although we were just talking earlier today, he hasn't really figured out how to retire yet. He's been very busy the last 6 weeks. Over these years of work, Dr. Bruckmaier has focused a lot on the field of milking physiology and the importance of oxytocin and other hormones in the regulation of milk ejection. The work from his group also contributed significantly to understanding the mammary immune response, including pathogen-specific differences of activation of different components of the immune system, helping to explain differences in the course of mastitis after infection with different pathogens. His studies on metabolism of high-yielding dairy cows show different adaptations across different animals as a potential basis for animal breeding, and also different endocrine adaptations to nutrient deficiency at the beginning of lactation. These efforts have led to over 300 peer-reviewed publications. Maybe you know the exact number. I couldn't easily find it. And he's been cited nearly 15,000 times, which is quite impressive. He's earned many awards. I'm not going to read them all off to you, but one of them was the American Society of Animal Science President's Award for International Achievements in Animal Science. And he happened to find a picture from when he got that award with last year's Tucker lecturer, Jeff Dahl. So that was kind of fun to see that. During all these research activities, he really focused on supporting young scientists that were in his team. And one piece of evidence in support of that is the person who took his role as head of veterinary physiology as he's retiring is Joseph Gross, who trained with Rupert for many years. So he was able to train his replacement. Furthermore, I can personally attest that Rupert has been very selfless in putting a lot of time into organizing international meetings over the years. I can think of 3 major ones just in the last 5 or 6 years. And some of us have been very fortunate to benefit from him hosting meetings at Bern, which is a beautiful city if you ever chance to visit. So without taking any more of your time, Rupert, thank you for being here and welcome.
Thank you. Yeah, thank you very much, Dr. Bradford. I'm also happy to be here. Thank you for the invitation. Nice also to see members of the Tucker family, even the youngest one, Hunter's daughter, obviously. So yeah, and it's a great honor to be here at East Lansing, where for many years I thought, wow, all the famous guys are coming somehow from this university. This must be a good place, but it's the first time I had the chance to come here. So thank you for the invitation. And I hope then it goes on. Yeah. So topic, advancing dairy production, select cows that fit our technology or develop technologies that fit the cows we have. This is a question of my talk today, and you will see Dr. Bradford said correctly, so I'm basically a physiologist, but you will see today I go very much into technology aspects related to milking. So to answer already the title question is, of course, we are doing both. We are adjusting cows to the needs of our technology, of the milking technology, but this is a very gradual process. But if we think over the last decades, so we need to think of decades, a lot happened with our cows with respect to production, but also with respect to the suitability of machine milking. And more recently, we are breeding just very silently for cows that are suitable for robotic milking. That means it had a very even distribution of the quarters of the udder. Technology is, I would say, this is much more challenging today because we can change this at the moment if we know what the cow needs. So knowing the physiology, the physiological requirement of the cow is basically the basis for adjustments of the technology. And this is basically the main topic what I want to go today. So some words about breeding for milk production and milkability, physiology of milking, just a few basics related to the oxytocin story for those who don't know it so exactly. Then also basics again on machine milking functions, milking machine functions. So let me know if it's boring for you to be too basic. Say, hey, go on. I just tried maybe to fetch everybody, also those who don't deal with milking every day. And then some current developments, which means also future developments to some aspect. What could be better in milking machines, in milking machine settings to optimize the milk removal. And with this, I think, of course, as in so many topics today, I think very much into artificial intelligence. So with new installations, if the machine knows the cow already and what to expect from this individual cow in this individual stage of lactation, then the milking process can be optimized. Okay, so, but again, let's start at the very beginning. Why is a cow producing milk? So, of course, to ensure the survival of the offspring. This is the only task. Which can be distributed in nutritional aspects. This is what we have mainly in focus, nutrition. And for the first weeks, actually, after birth of a calf, the milk is the exclusive nutrient. Later on, it is not. It's even so that the milk must become scarce for the calf, that the calf is forced to eat plants to become a ruminant. This is our problem with our lactation curve. You know, it's very difficult to breed for a high persistency because the design of the milk of the mammary gland function is that the milk production is decreasing. This is one of the things where the breeding was not that successful. Passive immunization via colostrum, and also an important aspect, mother-offspring bonding. We don't think so much on this in dairy farming anymore, unless that the function in the cow is very much directed into this mother-offspring bonding. But what is the offspring? The offspring is the milking machine today. And we have done studies really shown that the cows get very close to the milking machine where it is milked every day. If you change the milking environment or the milking machine, then you have certainly a few days of not optimal milking. This is related to this bonding effect. Okay. So the metabolic priority of the mammary gland is high. So it is relatively easy. I mean, geneticists or breeders would not say it's easy. I say, as a physiologist, I say it's comparatively easy to breed for high production because the metabolic priority is so high. And of course, if it comes to the business, to the dairy business, we want also fast milking cows. That means high milk flow. There, the breeding situation is not that easy because it's not so much controlled in the practice. The production is very much controlled with milk flow, milkability not so much. Anyway, and of course, there is a breeding for evenly structured udders that they just fit the milking machine. Now, this is the breeding side. And you can see what enormous progress the production, the annual production of cows has made now in this time during the 100 years from 1900 to 2000. Actually, Mike Vandenaar, so another MSU study, I guess, mainly at least, shows this increase of production. And what I found interesting here, from 1900 to 1960, it's a very slow development because this was only selection and with just regular interval of generations. So around in the 60s, it started to have much better, much more efficient reproduction managements. I mean, artificial insemination was starting at this time, embryo transfer. So this was, of course, shortening the generation intervals tremendously. And you see how steep the increase of production is coming during these last, let's say, 60 years, actually. And here are 10 years, 2013 to 2022, generally in the United States, and you see we are up on an average production per cow now at around 24,000 pounds, which is about 10 to 11,000 kilograms per year. Not so successful was the breeding with respect to the distribution of milk stored in the udder. So rear quarters have more milk than front quarters. It was a slight improvement from maybe 40 to 60%, now maybe to 45 to 55% in most cases. But this is just something I wanted to mention here because this is also related to the machine milking then, when the front quarters are empty while the rear quarters are still milking. And then some data, very scarce data on the development of milkability. So I made an evaluation of Swiss data in the area between 1963 to 1965 is when the milkability testing was introduced, very basic, no flow meters, no just cylinders where the milk per quarter was milked in and then the time was taken. And the average flow at this time was 1.7 kilograms per minute. But interestingly, they were also having the flow of the first minute, flow of the second minute, and so on. And it means that the maximum flow was about 2 kilograms per minute. That means the maximum flow was close to the average flow, which means if you have a milk flow curve in the mind, we would say this is more or less a rectangular curve. And we have also seen, even then in the later studies in the early 90s, that the flow in the rear quarters was higher than the flow rate in the front quarters. So that means the milking on empty teats in front quarters was not so tremendous. Also, we can see here in the 90s, we had an average flow rate in our study cows, 2.7 kilograms per minute, so already much higher than these earlier ones. But the maximum flow at this point was already approximately double of the average flow. So there is a change. And now allow me to move into Bavarian data. Bavaria is a state in Germany. And why Bavarian data? This is the only state where there is a complete control of the EMI via lactocorder measurements. That means they take the samples for the milk composition. They take also the amount of milk, but this system is recording complete milk flow curves. So every 2 seconds, it is a set of data on the milk flow. And I come back to this then in a minute, showing the development of milk flow curves. So Also, the Bavarian data show milk production increase per year, not so high as the US data are, but it's comparable. It's not so that far away. It's also, unfortunately, have this data only for the Fleckvieh, for the Simmental breed, not for Holstein, because in Bavaria there is not so many Holstein cows. So this would be a bit higher. And you see the milk yield per milking is increasing, not surprising, but the milking time has been the same during these years from 21 to 2023. That means, how is this possible? Is there then again a higher milk flow in these developments? And now I have the data also of these parameters. Over there, there is a milk flow curve. So this is what the milk flow looks like, an increase, and then you have a plateau phase. This is the phase of milking where all 4 quarters are running at full speed. Okay, and then there is a decline phase. Okay, decline phase, you can see this is usually a stepwise decline. Always when 1 quarter stops milk flow, you get a drop. And when the first drop is coming, this is then called a decline phase in these automatic recordings. The cessation of the first quarter is basically the start of the decline phase. So again here, average flow is increasing over these 20 years. Peak flow rate is increasing over these 20 years. But look here at the duration of the plateau phase and the duration of the decline phase. And this is kind of a bit of a surprise. The plateau phase is getting shorter, although the production is increasing, and the decline phase is getting longer. So that means we have a longer period of, in conventional systems, of course, milking on empty teats. At least one of them. This is, again, the decline phase is the period of the longest milking on empty teats, or at least of 1 quarter. So when the first quarter starts to stop the milk flow. And so this was then the reason also to look more deeply in the effects of this milking on empty teats. This was kind of a background now from the dairy farming practice. A few words now on the physiology, anatomy, physiology. So a cow has 4 quarters, independent glands, basically. Mastitis, people know that. If you're lucky, there's only 1 quarter infected. If you can prevent that, the bacteria are distributed about all quarters. So really independent, and 1 quarter has, each quarter has a cistern, a gland part of cistern, and a teat part of cistern. This is a small amount of milk which is stored in the cistern, and the majority of the milk is stored in the tissue, in the secretory tissue, in the alveolar tissue, which can be compared like to a sponge. This, to get the milk out of this secretory tissue, you need to squeeze it out. You cannot suck it out. So it's not an idea what some of the technology people have. Okay, increase the vacuum and we suck the other empty. You cannot suck the other empty. You can only get the milk which is in the cistern. And to bring the milk into the cistern needs a milk letdown. Okay? There is the famous hormone oxytocin. Some say this is maybe my favorite hormone. Yeah, maybe it makes happy and whatever. I have learned in the meantime. If I remember my times as a student, when I had to establish the assay and do all the extractions and the assay, I was not that happy about the hormone. Now I'm totally happy because I am done. I do not even know anymore where my lab is. My lab is the kitchen at home now. Okay, so oxytocin is released from the posterior pituitary, and it is, can I do something? Oh, warning. Flex. Huh? Advance. No. Touch this screen to extend. Oh, I did not touch hard enough. Okay. So In cows, we have about not more than 20% of the milk in the cistern, and most of the milk, 80 to 100%, are in the alveolar tissue. This is different in other animals, like in goats, it's just the opposite. Most of the milk is cisternal, so it's very easy. Milk let down, milk ejection is not that important that it happens timely. In cows, it is important. So here you can also see the alveoli. These are small micrometers, small structures, and there are myoepithelial cells which are contracting, and this presses the milk into the duct system and finally into the cistern. This is then the milk let down induced by oxytocin release, and oxytocin is released by tactile stimulation of the teats, or generally of the mammary gland, but mainly the teats. I hope that this works. I have just a super small video on ultrasound showing how the milk ejection looks like in the gland part of the cistern. So here is a frozen image, and here is a live image. And just to make sure that the letdown will happen, we injected oxytocin. And just to see, until the milk, the ejected milk, arrives here in the cistern, takes about 30 seconds. Okay, here is the clock running, so a few 10 seconds left. And here you can see how the milk ducts are entering from different sides here into the cistern. And now shortly we should see the milk entering. You see now it starts. We have this effect of the milk let down. At the same time, the cistern is enlarging, whereas the tissue, the secretory tissue, is just pressed, shifted back because it's partially empty. And then after another like half minute, this milk let down stops because there's an equilibrium between the muscle contraction of the myoepithelial cells and the pressure in the cistern. So the milk ejection will continue, but only when milk is removed, that there is more space in the cistern. Yeah. So these slides, sorry, a lot of text, but just a summary of oxytocin effects, because I want then in the further talk, I want to focus more on the technology part, so I cannot go too deep into all these oxytocin things. So oxytocin is a peptide, 9 amino acids, and the concentration is in the range between 1 and 100 picogram per ml, and mostly it's much closer to 1 picogram than to 100. So physiologically seen, 100 picograms per ml is already very high. 1 picogram is the lower level, and this is actually the reason that it's very tricky. So of the known hormones, this was one of the last ones where there was really a good radioimmunoassay. And if I say radioimmunoassay, it's until today, it is radioimmunoassay. There is not a real good alternative with a high enough sensitivity. So all ELISAs which are on the market, I would say all the curves which we see during milking, including increase in the ELISA, this is all background. So you do not even see an increase. So sometimes I do not really know what these ELISAs are for, but anyway, some people are using that. So the release in response to a tactile stimulation appears within 50 to 20 seconds. And then, of course, the alveolar milk is transferred into the cistern, and the first milk showing up at the earliest after about 50 seconds after the start of stimulation. And sometimes if the udder is really empty, it can be 2 minutes or even longer. This is not so relevant for milking, because a cow where the milk ejection takes longer than 2 minutes, I would then recommend dry the cow off. So, but if there's not much milk in the udder, it's that the case. So all this effect of oxytocin, the response when milk is showing up in the system, depends of the degree of filling of the alveoli. So the contraction. Okay. So this less than a minute, and I would say not shorter than 50 seconds, is important for those people who take milk samples. So if you want to have strict milk, only cisternal milk, you need to be fast to collect the milk from the 4 teats, because from the first touch onwards, of course, this initiation of oxytocin release is started. So you have maybe 40 seconds for sampling all 4 teats that you are sure that you have only cisternal milk. If you want to do bacteriology samples, you need much more time with sterilizing and so on. Do these afterwards. If you do bacteriology samples, each sample teat by teat, you will have a milk letdown at one point. What does not matter for bacteriology, by the way. If there are bacteria, it does not matter so much if it is strict cisternal or if it's already a mixture of cisternal and alveolar milk. For the milk composition, or for instance, for the cell count mainly, it matters because the first ejected alveolar milk has the lowest cell count in the whole milking process, and there's a relatively high cell count in the strict formilk. So also for the CMT, it is important to know what kind of milk do you have. So the sensitivity is much higher if you have strict formilk. If you have already a mixture of cisternal milk and alveolar milk, the cell count will already drop. And much more drop will be observed by the electrical conductivity. You know, this wonderful parameter, which does not cost very much, but is also not very reliable. So in strict formilk, it's not too bad, actually. But as soon as it's alveolar milk is in your sample, it will be down. So then you cannot detect mastitis. So, but just to move on from that, the milk ejection causes an increase of intercisternal pressure in the teat. And this is important also, or let's say it's ideal to touch the cluster when this increase of pressure is already there, because the fit of the teat cup is much better than when the teat is very soft. It will be sucked in for as long as the milk ejection is delayed. So pre-stimulation induces milk ejection, of course, already before milk is removed. And to avoid an interruption of milk flow, so the famous bimodal milk flow discussions, yeah, they are, in the meantime, they have arrived to US as well. At the beginning, the discussions were only in Germany very much, based on the lactocorda measurements. It's a bit so what, actually, I would say. There's alternatives also to prevent negative effects, even if the curve is bimodal. Oxytocin has a short half-life, 2 to 3 minutes only. That means the continuous stimulation is important. During milking, the stimulation is just done, continued by the movement of the liner. If oxytocin is decreasing, there will be a decrease of intramammary pressure also in the teat. That means a decrease, because this pressure in the teat has 2 components. It's just the column of milk, the height of the milk, has a certain pressure in the teat, but also the muscle contraction, the myoepithelial contraction presses on this milk. And there is an additional part of like 1 or 2 kilopascals pressure in the teat, which is has some importance. And so this pressure must be maintained. And therefore, it's important that oxytocin is continuously released. That means long interruptions between kind of a prep or whatever happens until finally the cluster is attached should be avoided. Long interruptions means for me like more than 2-3 minutes. If the interruption is 1 minute, nothing happens because oxytocin stays elevated during this period when then the stimulus comes back. But this is all, of course, physiological details. I cannot go too deep into this now. So another ultrasound presentation just showing in one individual quarter, the cistern size stays pretty much the same until it is finally empty. And here you can see this is a milk flow curve, a total milk flow curve. And you see the first quarter is finishing here. So the decline phase starts here of this milk flow curve. You can already see in this curve, half of the milk flow curve is decline phase. So this first front quarter is already finished here, and then individual quarters are milked, but this first one is already milked empty. And you can see on these dots here, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, the cistern is continuously refilled from the tissue because this pressure of the contraction of the meioepithelial cells is maintained. So you do not see a difference until finally this quarter is empty, and then it looks like this. The cistern is disappeared, or let's say it starts already here to become smaller here when really this 1/4 is stopping the milk flow. And of course, to show also what happens in a bimodal curve, this is a typical bimodal curve. So this cisternal milk is removed here, and then by the stimulation of the liner movement, milk ejection is induced, and here is the start of milk ejection, and the milk flow goes up. This is a typical bimodal curve. First the cisternal milk, and then the alveolar milk is coming separately. If you look here in the pictures, 1, 2, and 3, you see during this time when the cisternal milk is removed, we have already here a disappearance of the cistern. That means at this point, we have an empty teat. And the effect, what we have always at the end of milking, in this bimodal curve, in these extreme bimodal curves, if there's just a full vacuum is continuing, then we have already this negative effect of really sucking the teat into the liner, because the seal and the adhesion between the liner and the teat is not strong enough anymore. And then when the milk ejection occurs, you see the remaining pictures here, then the cistern gets again large until the quarter is empty. But just to show, we have basically in this very strong bimodal curves, we have like an end of milking situation already shortly after the start of the milking, which is not ideal. I would say with some technical adjustments, it does not matter so much. I am coming to that. So the evolution of milking, what I want to show you here is the first drawings is like 5,000 years ago, milking, and you see they have the calf with the cow, otherwise maybe these cows at this time don't give very much milk. We know this type of cows are still in the Shami cattle in Syria. Unfortunately, not a real place to visit today, but I have been years ago, and there is the same situation. If you put the calf away, they are not really happy to give the milk during milking, but with the calf they are. Anyway, so 4,000 years ago, and then hundreds of years ago, all these pictures look pretty much similar. There's not much of a development in milking technology until, let's say, the middle of the 20th century, when then the machine milking started. And so basically, the machine milking started 100 years ago, exactly with the same system what we have today, with a double chamber teat cup with a pulsating liner. So it was already seen at this time that a stop and go of the milking, that means an intermediate closer of the liner to massage the liquid back of the teat tip, is better than a continuous suck. And it is true. I mean, you can also milk cows without pulsation, just suck them empty. But this, and they will be empty also, but this takes longer. And the teat does not look very good at the end. So with the pulsation is definitively, this was the invention which helped the milking technology. But then everything went very slow. In the 1930s, there were this type of facilities. So all bucket milkers, and only, at least in Europe, only the really large farms had this type of personnel and also these bucket milkers. And at least in Germany and Switzerland, machine milking was started in the 60s. There was not much going on before at this time. And at this time, this was all bucket milkers. And interestingly, I mean, I can tell you, we are doing our experiments with 10 cows or so with ultrasound and vacuum measurements and milk flow measurements in a stanchion barn with bucket milkers, because this is the best you can do. Just not for the farmer who has always to empty the bucket. But the line, whole milk line is not transported somewhere into an elevated position. It stays all just at the height of the other level, and the tube can be short. So you have a minimum loss of vacuum, and the story is about that. So mainly in the 70s, at least in Switzerland, there was a lot of highline systems installed. Okay, this was at a time when the milk flows were still not so high anymore. The problem is at full milk flow, you need to transport all the milk 2 meters upwards, and 2 meters upwards, if you just count the liquid column, anyone has an idea how many kilopascals you're losing? No. Okay, so a liquid column of 2 meters means 20 kilopascal. So the whole thing is in move, so it's not 20 kilopascal, but easily 10 to 15 kilopascals. Then, I mean, with such a system, if you have a really high milk flow, that means you need to set your vacuum. If you have only one vacuum to set, you have to set it high enough that you have still enough vacuum during this high milk flow when you when you lose the vacuum, when you have the drop. Okay, and that means in tie stalls today, they go to 50 kilopascals or more. All good during peak flow, then you have still 30, 35 kilopascals. But if there is no milk flow or a bimodal curve, then you have the 50 kilopascals on the teat. And this is too much. This will really cause enormously swellings, congestion on the teat, because there is not only the suck by the vacuum, there is also the compression of the liner. You know, the vacuum on the teat and side, inside the liner, has the two tasks: sucking and compressing when the pulsation chamber is vented. So this is just too high. So I would say today in a cow with a milk flow level, what we have today, at least average flows of 4 kilograms per minute, highline is the past, no longer possible. And then, of course, parlors were increasingly coming up in the 1990s, and then they have low line or midi line. I mean, midi line, we just discussed this before this morning. In Ireland, there is a system which is midi line. Okay, in Ireland, this certainly works because the milk flow in Irish cows is really very low. Same like in New Zealand. So they have peak flows of 3 kilograms per minute or so. Then you can go with that. But in high flow cows, even midi line is not ideal. So low line means all the milk from the cow to the, let's say, to the tank is just going downwards or just stays at the same level, but there is no upward transport. Okay, and then of course the newest developments is started around 2000. Robotic milking means this was the first time that quarter milking is possible. So each quarter separately is possible. In the conventional, you know, you have one cluster where all the four teat cups together have to function, and this is not so easy. Of course, there is also then developments like these rotaries, huge rotaries, but this is basically from the point of view of the cow or of the udder, these are low-line systems, okay? Huge, of course. It's possible today, and also automatized possible. So also quarter milking in rotaries is possible basically, but this is just in a time now where this is coming up. So just for those who are not so familiar with the function of a milking machine. So we have a teat cup, which is usually made from steel. The reason is it must have some weight to prevent the clamping. And inside is a liner. And between the steel cup and the liner is also a space. And this is the pulsation chamber. And the pulsation chamber is either vented, like here, or evacuated. In the pulsation chamber, this is what you hear when you go in the barn. This tuck, 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 tuck. This is the pulsator. This is basically the alternating effect, what you can see also here, liner open or liner closed. So open the liner is open when the pulsation chamber is evacuated, and the liner press. When the pulsation chamber is evacuated, then the liner is open. And why is it then collapsing when the pulsation chamber is vented? Because on the teat end side, inside the liner is continuous vacuum. Okay, so this vacuum sucks, and when outside the liner is atmospheric air, the liner will just collapse. But this functions only, of course, when the vacuum on the teat end side is high enough. So at some point, if it comes to like to 20 kilopascals, because the milk flow is so high, the liner will not close adequately anymore. It will stay partially open. At least it will not do any massage effect, which is so important. You can see this. I cannot show this video now from ultrasound, but you can see when the liner is closing that the milk is coming a bit back out of the teat. So there is really closure here of the teat tip, which presses a piece of the milk back to reopen also all the ducts, that when the liner reopens, that the flow can really be fast again. Okay, that's the effect. And just showing this kind of graphic here, when there is no milk flow, we see, of course, the teat end vacuum is as high as the pulsation chamber vacuum. So this red curve is the pulse curve. When the pulsation chamber is completely evacuated, these are both vacuum levels are the same, and the liner opens here and closes here. And beyond closure, there is pressure on the teat. This is the pressure then here when the pulsation chamber is completely vented. During milk flow, just as a model here, you see the pulsation vacuum is the same, but the teat end vacuum is decreasing because the milk needs to be transported, which means the liner is opening much earlier and also closing later. And the spare vacuum here, which means for the teat is an additional pressure of the closed liner here, is much less than it would be here. And that is the reason that if, for instance, extremely in a highline system, the vacuum must be set high enough that we have still enough vacuum here that the liner compression is working correctly when the liner is closing. Okay. Okay. And just you see what kind of crazy experiments we are doing. This was a test, different milk flow levels, and how much would be the vacuum drop, high line compared to low line. And to have a continuous effect here, height of the bucket, we use the same bucket, the same tube, everything, and we just pull the bucket up to see what is the effect of vacuum loss at different flow levels and height. And you see we have a tremendous drop if the bucket is 2 meters high, and this is basically at a flow of like 6 kilograms per minute, the vacuum is already too low. So the heat does not function anymore very well. Okay, recently we have done more experiments also, not only measuring the teat end vacuum. You can also see here the blue curve is a vacuum, the vacuum curve which drops in the low line system. There is not much vacuum drop. It's just a normal one just by the transport of the milk flow here, or of the milk. When the milk flow decreases, the vacuum on the teat end side is going up back to the system vacuum. But in addition, this is more in focus now recently, also because the technical equipment is available to measure the mouthpiece chamber vacuum. And here is the mouthpiece. As long as there is a high pressure inside the teat, the adhesion or the seal between the liner and the teat is very high. And because the liner lip here on the top is always leaking slightly, we have a very low vacuum here in this mouthpiece chamber. And this is important that to prevent the climbing of the teat cup. There's a low vacuum part here on the top of the teat cup. So when this particular quarter is empty, this seal is lost. okay? And we get an increase of the mouthpiece chamber vacuum. This, first of all, is not good for the teeth. So if this happens too long, you can really see a swelling on the teeth exactly at this position of the mouthpiece. But at the same time, this increase of the MPC vacuum is a marker for the stop of milk flow by quarter, which we don't have so nicely in conventional systems. In robots, of course, we have it. So as a marker of the end of milk flow in an individual quarter, we can measure the 4 mouthpiece chamber vacuum levels. And it's very easy today because there are sensors available, which is just the signal is transferred with a Bluetooth. I almost said blue tongue, but Bluetooth. It's Bluetooth transfer. Exactly. So, and it's a nice indicator also to optimize the milking procedure. So, of course, what we are searching for is an optimal interplay between the squeeze on the cow side, so the milk is pressed into the cistern, and the suck of the machine side. So with the squeeze, we cannot do very much. Pre-stimulation is the only one, but with the suck, we can adjust to the continuous changes of these squeeze effects, okay? And I just say, I mean, the teat preparation is the start of milking. Okay, we can prevent the transient over milking at the start of milking. So pre-stimulation would be the activity to do, or just alternatively reduce the vacuum as long as there is only little milk available. Or what is the vacuum reduction is not usually performed in the US. It's just a very short liner open phase. So the reverse pulsation ratio means the liner is just open for a short moment, but mainly most of the time it is closed. And this works. Actually, there you don't see any hurt then and any congestion in the teeth if such a thing is applied. So during the main milking phase, first of all, it's important to know when is congestion or thickening of the tissue happening. During milking, just one small study here, during the whole milking process, almost nothing happens, very slight. Over milking, that means milking on empty teeth, then it jumps up. That means the end of the milking is the critical point. The end of the milking on empty teeth is the thing to be prevented. So activities, of course, limit the vacuum drop during this period, that you have an adequate massage. I would say no high-line milking in a high-yielding and high milk flow cow. Milk flow controlled vacuum pulsation. And early detachment. So I will be smoothly go up to 1 kilogram per minute. I say this here in the United States. I'm far away from Switzerland. So in Switzerland, we have a detachment 200 grams, and it is almost not possible to change that. And of course, quarter milking as far as is possible. To some extent, it can also be done in conventional systems by using the mouthpiece chamber vacuum as a marker and then reduce partially the vacuum. So it seems that I'm, for whatever reason, a bit late. I just wanted to show you a few experiments here, what we did to show the things what I was just mentioning here, and I can go maybe very quickly over it. We went with a vacuum up to 53 kilopascals on the teat side, but during low flow, we reduced to normal vacuum. And with this, we could prevent all negative effects on the teat tissue. So you can go very high with the vacuum, maybe up to 60 kilopascals, as long as you go down with the vacuum when the milk flow is so low that the teat is kind of squeezed because the pressure inside the teat is lost. So we switched down with the vacuum just if the flow was less than 2 kilograms per minute on a whole loader basis. Okay, and then high detachment, of course, up to 1 kilogram was just perfect to shorten the milking time, and there was almost no milk left in the udder. So this is easy, and I jump over this result slides, and just maybe this last one to show, increase the pulsation ratio in the hind quarters, in the rear quarters. That means we milk the rear quarters faster than the front quarters. Done here. So front quarters always 65 to 60 to 35 ratio. And then in the rear quarters up to 80 to 20. And surprisingly, nothing happened because these rear quarters are not over-milked, because the detachment will happen when they are empty, because they milk anyway. Still a bit longer, but you can see all this decline phase, we could really tremendously shorten just by increasing selectively the pulsation rate. And this can be easily done in conventional systems because it needs just a special 2 different pulsation tubes, one for the front quarters, one for the rear quarters, and that's it. And inside the heat cup, it's basically the same what happens. Anyway, conclusions. I go very quickly to the last sentence. Perspective, the use of artificial intelligence is always a good way to argue. Introduce artificial intelligence and you can solve all problems as soon as you know what the problems are. And so therefore, I see our task as physiologists, tell the technology people what they need to do, because they think everything is so easy. I mean, the cow is a biological individual, and we should recognize that. And yeah, that's it. And just my last picture here shows, I hope that it was not that boring as it was for the cows here on the pictures. Thank you very much.